Thank you very much, Marta. I wanted to first thank the organizer of the workshop for inviting me to give a talk at this very interesting workshop. And well, like Christina said before, I would first of all like to define the context and the reason why we are talking today about physically assistive robots for ambulation and walking and balance. As you know, Europe and the world in general is experiencing a significant increase on the percentage of older population. And in England, 74% of these older people require support with physical activities. But it's not only about older people, which a lot of people try to focus on, but there is also a younger population with different physical and mental disabilities due to illness, accidents, or trauma that need physical support. In England alone, 29% of younger population require physical support. And this need of support is suffering from the reported shortage of staff in hospitals, mental health services, community providers, which is creating a big socioeconomical impact. It not only directly affects the quality of life and the quality of care that people needs and is having, and their possibilities of independent living, but also looking at the cost. Only in UK, long-term support expense last year was estimated around 15 billion pounds. Therefore, there is a need of an urgent need of assistive technologies to allow the people in need of care to maintain and regain functionality, so we can create a sustainable community active in society. So this was just to create a bit of context of why I'm talking today about physically assistive robots and why this is of interest to me. And among the many types of assistive robots that can provide support, we focus on those. Today we're focusing on those that can provide physical support, and specifically physical support for balancing and walking. This can be external platforms such as intelligent walkers or canes that previous presenters have been talking a lot about it, exoskeleton devices, or even prostheses. However, most of the implemented solutions that we find nowadays in the market, when they are brought to the real world, they all face similar issues that ultimately lead to abandonment of the device. Actually, 7 out of 10 people tend to abandon their assistive technologies, and around 22% of lower limb prosthetic users abandon their device within the first year of use. Christina before just mentioned some of the barriers, talking about the intelligent walkers, and some of them have to do with the design and function, with the information and awareness on the use of the device, the service provision, this maintenance, psychological barriers, the support network, and of some societal barriers as well. Focusing on the design and function of these devices, which is where we can put more effort as roboticists, issues to point are the lack of a user-centric design, the lack of the possibility of customization. A lot of users report that these devices are not easy to use, that they lack predictability, functionality, they are too heavy or too light, they are uncomfortable, they have high purchase and maintenance costs, and the lack of sensory feedback is also pointed as one of the main issues that prevents them from continuing using these devices. Many of these issues are related one way or another to the concept of adaptability. That is, having a device that can adapt to different functions, shapes, interfaces, tasks. And the reason for that we need this adaptability in assistive robots is that assistive devices are, first of all, used in unconstrained and unpredictable environments, in daily living activities, in homes or on the streets. They are not going to be used in a controlled lab environment. And second, they are going to be used by humans who are by nature diverse from each other, with different ages, different heights, different weights, different body shapes. So adaptability to all these to this environment and this different type of people is a key enabler, because also not only in terms of environment and of body shapes, also people behavior can vary between different persons, and this whose also condition can progress or can regress, and they can get better or worse. So not being able to adapt to their continuous evolvement can result in maybe weakness of the user. So if you provide too much assistance to a person, they might end up relying on the device and becoming weak themselves, or reduce motivations if you provide the wrong support, or if you provide too little support and this results in the person not being able to complete their task. This will reduce their motivation and end up again giving up the device. So better adaptability can enhance intuitiveness and natural use of the device, and also endow the robot with partial autonomy, which unloads the user and even sometimes the carer from the burden of regulating the device. So what I propose, or what I'm talking in this presentation, is about the possibility to achieve this adaptability through bioinspiration. So bioinspiration is not really biomimicry. Bioinspiration is the development of novel material, devices, structures, control, inspired by solutions found in biological system and biological evolution, and the refinement which has occurred over millions of years. And in technology, this inspiration is used to design novel and more efficient and intuitive devices. So I'm going to focus on the idea of providing adaptability through bioinspiration, not on the design of the devices, but on the way that we control these devices to provide support in ambulation. So these two examples, we studied human motion for the first one was about controlling leg exoskeleton, and the other one was about studying sit to stand motion. So I'm gonna give details of these two particular studies. So the objective of the first work, this was a collaborative project between several universities and research centers, and the objective was to control a lower limb exoskeleton that could generate a stable patterns of locomotion, that also could handle different tasks and also transitions between these tasks. We focus on walking at different speeds and being able to go upstairs, downstairs, and being able to seamlessly transition between this walking and upstairs, not having to stop between one task and the next. And that would be able to adapt to different users. In this case, say we are focusing on the control part. So when I say adapt to each user, I mean adapt to their particular way of walking or ambulating, the way that they behave in a personal level. And of course, that part of the objective that is would be able to effectively assist. So we looked at to see if there was a reduction of the energy consumption when using the device, and that it was able to be used in different platforms. So we wanted a controller that in the end just output joint torques for the lower limb exoskeleton. So it could be afterwards put in any type of device that could be controlled by torque. So to develop this bioinspired adaptable controller, we started taking inspiration from the central pattern generators in the human body. So central pattern generators are defined as neural oscillators that are located in the spinal cord of mammals, and they can be considered the source of rhythmicity in locomotion. They can provide rhythmic excitation to the muscles, even if receiving non-periodic inputs. In other words, they are considered to be the biological clock for rhythmic movements. For example, when you are walking, that is a rhythmic movement. So the CPU is the one giving you the clock, the timing, the frequency of that walk. from the concept of central pattern generators, the one of motor primitives and sinews arose. All of these concepts are tightly interconnected. The CPGs, as we said, are considered the sort of rhythmicity, like the clock of the movement, but we still need the actual muscle activation signals that will produce the movement, the ones that will make our muscles contract. So to generate all those signals, if you can see in the diagram on the right, these are around 16 muscle signals that we have in our lower leg. And all of these, you have to activate these muscles from both legs. So that goes to 32. And you have to do that in a coordinated way. So everything is sequenced in perfect timing. So you can keep balance and the movement that is output is meaningful. And there were many studies that these several types of signal decomposition into these EMG, these muscle signals, and they found out that actually a very few amount of signals could explain the whole variability of muscle activations during walking. And these basic signals, what I actually here, you can see 6 of them, are motor, what we call motor primitives, and they are physically encoded in our spinal level. So the idea is that by using a small subset of very simple signals and combining them in a very simple algorithmically way, we can create all necessary muscle stimulations in a coordinated way to produce cyclic movements. So similar to primitives, there is the definition of synergies. Sometimes these two concepts are confused and are used in place of the other, but I like to define synergies more as at the muscular level. And they are described as the coordinated activity that arises from the activation of the muscles. So it is somehow the resulting coordinated movement from the input of the motor primitives. So if we think about using these concepts for our control, we started by trying to emulate very high-level commands in a simplified way, just by having as external input for the controller the desired locomotion task to be performed. This was developed within the University of Ljubljana, and they perform sensory fusion algorithm that was able to output whether the person was intended to walk, to go upstairs, to go downstairs, or if the person was standing. Then afterwards, we emulated the central pattern generator, so that biological clock, by the use of adaptive oscillators. We synchronize the adaptive oscillators to the hip movement, and these oscillators are able to extract phase and frequency characteristic of the movement. So if okay, in the case of an exoskeleton, we were able to track the hip movement and have the oscillators linked to the movement of the hip. But if you're thinking of an autonomous model, you could also force a desired value and generate a phase signal. Then we created the set of artificial primitives that try to emulate the biological ones. So the idea is to have a few set of primitives that can be recombined using different weights in function of the inputs of frequency, phase, and locomotion task, and then output some feed-forward stimulations for the muscles. So I'm going to briefly explain how we obtain these primitives. So we did first a broad literature search, and we did some optimization algorithms based on literature data we found on torque and kinematics for different walking and stair ambulation activities. And we gather from this genetic algorithm optimization muscle stimulations for a simplified leg model that consisted of 7 muscles. And we analyzed 5 different walking cadences and movements for ascending and descending stairs. So in total, if we have 7 muscles, 5 walking cadences, and the standing stairs, we ended up with 49 muscle stimulation signals. And these, we all normalize all of them as a function of the gait cycle. And we used the composition process to obtain our motor primitives. So we managed to do a dimensionality reduction from 49 signals to 6 motor primitives. And the idea is that these primitives combined in different proportions, which are the weights, can reconstruct all those 49 stimulations for the different walking cadences and locomotion tasks. So if we see it with an example, if we want to, for example, reconstruct the muscle stimulations needed to perform stair ascending, we'll take our primitives, we will take the set of weights that are needed for stair ascending. And if we think, okay, I want to know how the soleus stimulation could be, we select the weights that correspond to the soleus muscle. And well, in this case, they mainly use 4 of the primitives. And then is a matter of doing a linear combination. We multiply the first primitive by the first weight, the second primitive by the second weight, the third primitive by the third weight, and so on. And we obtain the soleus muscle stimulation. And we do this for all the muscles to obtain all the muscle stimulations needed for that particular task. Then if we come back to the controller components, these stimulations enter the simplified musculoskeletal model that consisted on 7 muscles. And just bear in mind that this model is virtual, so it's not implemented in the exoskeleton. We don't have a muscle-driven exoskeleton. We have a joint torque-driven exoskeleton. So the activation of these virtual muscles eventually create the virtual joint torque, which a proportion of which can be used to drive the exoskeleton depending on the desired level of assistance. Finally, we also try to emulate in a very simplified way the feedback afferents. So we have the feed-forward part coming from the primitives, but we also have, we also have the reflexes. And we had a set of short loop reflexes and a torso balance mechanism that also generated muscle stimulations that we could add to the signals coming from the primitives. So if we combine all of the components we just described, we arrive to our proposed controller. We display it in a more classical way here. So we have the intention detection, the oscillators, the primitives combined entering the muscle and going to the human exoskeleton. So importantly, this controller presents 3 levels of adaptation. First, the primitives are output depending on the gait phase. So they follow the pace of the person while walking. If the person is walking faster, the assistance is going to go faster as well. Second, depending on the walking cadence and locomotion task, primitives are combined using different weights, giving rise to the required stimulation profiles for each case. And finally, the musculoskeletal model adapted these stimulations depending on the actual walking pattern of the person. So there were the kinematics, the real kinematics measured from the person, enter also musculoskeletal model. So if the movement pattern from a particular person is different, the joint torques will also differ. For the experiments, we focus on the assistance being generated by the feed-forward simulations coming from the primitives. And we did 3 different experiments. The first one only focused on the hip assistance and measuring the oxygen consumption and checking that there was an energy reduction. The second one was a proof of concept that we tried the hip exoskeleton with an amputee. And the third one was a more complex scenario in which we did level ground walking, a stair, going upstairs, turning around, going downstairs and back, a whole circuit. And using the full leg exoskeleton, and it was envisioned to test all the different transitions and adaptations of the exoskeleton. So on the left, you can see the experiment just on the corridor. So it was the 6-minute walk trial. And on the right, there is, oh, yeah, on the right, there is the motor primitives. I don't know why it's not running. This one. Okay, well, anyway. So in terms of locomotion effort, of course, we could see that this is the condition where people were not wearing the exoskeleton, and there is, of course, a big increment the moment that you put the exoskeleton because of the weight of it. The important thing here is to see that we saw a significant reduction in oxygen cost when the assistance was provided. That was not so evident in case of the person with the prosthetic, but we also saw that there was an increment in all of the vital measurements as time passed. So we thought probably has to do with a fatigue effect. In any case, one of the things we observed that was that, especially for ground level walking, even if there was not a big decrease on the heart rate or ventilation or oxygen consumption, the speed of the person was significantly reduced. Sorry, the speed of the person increased significantly, which means that even if they were using more energy, they actually walk faster than without the assistance. And in the third experiment, with all the track and the stairs ups and down, we couldn't measure the oxygen consumption. So what we did was to measure the time it took for the people to complete the track. And we could see, again, that from not wearing the orthosis to wearing the orthosis, it incremented, but there was no assistance provided here. And the moment we provided the assistance, the people were faster in completing their track. Then talking about the adaptability, first, that was mainly what we saw in experiment 3. We could see that the system was able to adapt to each locomotion task. And we could see how the different primitives were combined to generate the different stimulations needed for walking, stair standing, or stair standing. And also, we could see that it could provide the transitions quite smoothly. So the whole system could adapt in less than 2 cycles on changing from stair standing to walking, and from walking to stair standing, you can see the changes in the hip, knee, and ankle torques moving quite differently and fast from one task to another. And primitives were also differently combined depending on the gait cadence. So if you see, for example, subjects 6 and 7, which are the green and dotted black, these were the slowest participants. And if you can see, the hip flexor stimulation is also quite lower when walking with respect to the other participants. And the third is the one important one is about adapting to personal way of moving. So the natural pattern of each person. So if you can see, these are the knee angles and the knee torques generated. And subject 2, which is in dark blue, had no knee flexion during walking after heel strike. So subject 2 kept their leg completely straight when they did the heel strike. So there was no need to generate a knee extension torque. And that's what we can see, that the control didn't generate any knee extension torque. Instead, for subject 3, there was a flexion in the knee. So we needed to extend the knee, and the controller did do that extension. So quickly moving into the second work, which is still ongoing work, the idea that we have is, well, in the future, to generate some adaptive sit-to-stand hoist trajectories for people with a stroke. So nowadays, this is how hoists are used. Sorry, So they are quite cumbersome to use. They are manually they're manually driven. They provide like a fixed trajectory up, so don't adapt to the user, and they need usually two assistants. So what we want to do is to generate robotic hoists that can do also personalized assistance to do sit to stand, because, well, in order to walk or to do any type of ambulation, first you need to stand up. So we had two main objectives within this project. The first one, to use the biomechanical analysis to understand how people actually do sit to stand and stand to sit. And we're focusing on people with stroke patterns, and also to see if we were able to predict a trajectory that could focus on informing a user-centric design, adaptive control design for assistive robots. So the idea is that if we have a person with a stroke that has a particular way of standing up, and we know how that person ideally should be able to stand up, we can generate a trajectory in between that gently pushes the person to an ideal trajectory. So we measured 24 people without a stroke doing sit to stand movements, 6 people with a stroke. We did 20 repetition different seat heights, and we measured the balance board. We measured the kinematics of the people, and we used a pressure mat. For the non-stroke participants, one of the things we observed was that a similar amount of force was applied on each side of the body during sit-to-stand motion, while for the stroke patients, there was a lot more weight put on the stroke effect on the unimpaired side, in this case, the left leg. So we can see an asymmetry, and this asymmetry between the functional and impaired leg comes at the moment when the person is shifting the weight from being seated to the feet. So it's this moment when you need more balance, when they rely more on their functional leg. And I forgot to mention that also there is, just at the beginning, you can see comparing the stroke patient with the non-stroke patient, we can see that the stroke person had, there is a release of weight. So there is a moment when the person lifts the feet and then pushes up to create that impulse to stand up. So there is a sort of rocking motion that the person does to create dynamic movement that helps them balance. Also, using the balance board, the pressure board, we can see how a stroke people with a stroke had larger displacement in X and Y direction on the center of pressure, demonstrating that they struggle with balance. And actually, these big displacements in a space can generate a greater risk of fall. Instead, non-stroke participants generally showed very little displacement in X and mainly moved in the Y direction, in the sagittal plane. We also studied the pressure mat, and we could just see that people with, again, with stroke had an asymmetry between the way that they are shifting the weight when moving from sit to stand and from the stand to sit. And also they were faster in the way that they were standing up. So they generated a lot of velocity and passed from being seated to not being seated in a much faster way. So that is what we understood from studying the way people do sit to stand. And the second objective was to do a trajectory prediction, focusing on how we could use a robotic assistance. So what we did was focusing on the way that people without a stroke were doing the sit to stand, because again, we want to base our controller on an ideal trajectory. So we did average of trajectories, and we did a model that was based on height, weight, and age. And the idea was, well, what do we use as a trajectory? So most people use the center of mass as a predictor because it can detect very well when there is a risk of fall. But computing the center of mass is computationally expensive, and a lot of people end up using simplified models, which in turn affect the accuracy of the prediction. So we thought, okay, we're going to do a robotic model. We're probably based on something like vision sensors. And most of the vision recognition sensors use key markers, and most of them, one of the points are the shoulders. So we decided to use the mid-shoulder trajectory to be predicted. So the objective is to obtain a simplified prediction algorithm that needs as few variables as possible to retrieve a personalized user trajectory. We focus on the sagittal plane, and we assume that the robotic support will be predominantly in the vertical direction. So we used a k-nearest neighbor algorithm, and we use as coordinates first the weight and the height, and then we did the body mass and the age. These are the results in terms of coefficient of determination. And in general, what we could see is that the algorithm was able to better predict sit to stand movements rather than stand to sit movements. And we think this is because probably the sit to stand movement is a more controlled movement. And when people are standing and then sitting, there is a bit of a free fall sometimes that creates more variability on the movement. And then we used we did an example using 3 neighbors for the prediction of people with a stroke, and you can see here the results. So you can see there is a big difference in many of the subjects, but this is okay because, as we say, we are not trying to predict how a person with a stroke was moving. We are trying to predict how they would move if they did not have a stroke. So for example, subject 1, there is a big difference in the way they actually move and the way that we predicted they would move. And we think it's probably because subject 1 was more impaired than, for example, subject 3, where the prediction between an ideal trajectory and the actual trajectory of the person are more similar. So this is something we keep on working, and we hope to develop more in the future. We have the basis for a controller, and now we are working on the development of the actual system that can implement this controller. Also wanted to say that all of these data that we recorded for sit to stand is open, and you can find it on our GitHub, and we would be very happy if people would contribute to this data, because yeah, we saw that there was no available open source data for sit to stand. So just wrapping up, I would say that physically assistive robots for ambulation are needed as there is an increase of physical support. And current assistive technologies are usually quite cumbersome. They are difficult to use, and they eventually get discarded. So we think that using bioinspiration can provide a stable profile for controlling these devices that can adapt to the different people and their different needs, and that can be more natural and intuitive to use. So I just wanted to acknowledge the people in the lab. Thank you very much.